tail tests are very useful, and they're very much a part of the way modern scientific research is done. But they have some fishy aspects, especially from a Bayesian viewpoint, and we want to talk about 3 of those in this segment. The first odd thing about tail tests is that the result depends on the choice of the test. You had to choose a test statistic in order to compute what its p-value is. And more argumentatively, you can find examples where the result of the test seems to depend on not the actual results of the physical world, but what was in the mind of the experimenter. These are called stopping rule paradoxes. And let's examine this by giving an example. So suppose the hypothesis, the null hypothesis, H0, is that a coin is a fair coin, with the probability of getting a heads being 50%. And now we watch an experimenter flip coins. Maybe we're watching this only on a video after the experiment took place, and we see the data unfold. And the data is that the experimenter flips the coin 10 times. The first 9 times it comes up heads, and then it comes up a tail. So how do we turn this into a p-value test? Analysis method 1. Data as extreme as we've seen, namely 9 heads and 1 tail, should occur under the null hypothesis only this often. How do we compute this? Well, there are 2 to the 10th possible outcomes of the experiment. That is, each of 10 flips could have been a head or a tail. In one of these outcomes, we get all heads. In one of these outcomes, we get all tails. And then in 10, we get what we actually saw, 9 heads and 1 tail. And equally extreme, we could have gotten 9 tails and 1 head. So the probability of an outcome as extreme or more extreme than we actually saw is this expression, which turns out to be a little bit more than 2%. So you write this up and you send it into the Journal of Obscure Head-Tail Flipping Results, or whatever journal it is you're submitting to, and the referee writes back and says, no, we're not going to accept this paper because you have a significance level of only 2%, and we wanted a significance, a p-value of less than 1% is the standard that our journal upholds. You go back to the experimenter. Oh, I forgot to tell you, the experimenter says. My protocol was that I was going to flip a coin until I got a tail, and then I was going to record as n the number of heads that I got before I got that tail. So you say, oh, I should have done the analysis differently. Here's analysis method 2. So let's analyze this. Under the null hypothesis, the experimenter is going to record the number n with probability 2 to the minus the quantity n plus 1. How can we see this? Well, he's going to record the number n if there have been exactly n heads followed by exactly 1 tail, which stops the experiment. So there are n plus 1 flips of the coin that have to come out in a particular way, and the probability of that is 2 to the minus the quantity n plus 1. Now we want to compute the p-value, which is the probability of seeing results as extreme or more extreme than n. So that will be the probability of, we can write it as greater or equal to n. And what should that be? Well, the probability that it's equal to n is this 2 to the minus n plus 1 times 1. And then the probability that it's 1 larger than that, more extreme, would be a half of that value. The probability that it's 2 larger would be a quarter of that value, and so on. And of course you know that this sums up to exactly 2 as an infinite series, and so the answer is 2 to the minus n for the p-value. So therefore the p-value in the data that we actually see, the probability that it's greater than or equal to 9, is 2 to the minus 9, and that's 2 parts in 1,000 approximately. That's a much more significant result than analysis method 1 gave. So you win. You write back to the referee with this new analysis method, and your paper gets published. That seems a little fishy, doesn't it? That you can get two different levels of significance depending on, first of all, which analysis method you chose, but second of all, what protocol the experimenter was using. And if you simply had a video of the experimenter flipping the coins and were trying to decide on the basis of that video what the significance level is, it would be entirely ambiguous because you wouldn't know what the stopping rule was. Now, stopping rule effects are actually a serious methodological issue in biomedical research. And the reason is experiments have to be ethical. And an ethical experiment has to be stopped if it's harming the patients who are the test subjects in the experiment. And you may not be able to anticipate in advance of planning the experiment all the ways the experiment might be stopped. And therefore, you can't predict in advance exactly what the right way to analyze the data is. That's a serious methodological flaw because you can't simply set out to do an experiment by a fixed protocol. Here's a famous example of a few years back of a drug company that had a protocol for testing a drug for safety. I'll let you read this at your leisure, but I'll just give you the key point here. The protocol, for some reason or another, was that they were going to try the drug out on 6 healthy individuals. So they tried the 6 healthy individuals, and it was a disaster. They almost killed them all. We might look back on this with hindsight and say, well, why didn't they try one individual, and then when they saw that it was safe on that individual, then try the second and then try the third? Well, probably it's because they were doing a p-value test on the result, and they had decided in advance that they could get a significant result for the safety of the drug, or a significant enough result, only if they had 6 subjects, and that was their protocol, and they were sticking to it. And as it says down here, the company emphasized that they had complied with all regulatory requirements and conducted the trial according to an approved protocol. But p-value tests, we see, are rather rigid in protocol if you want to avoid stopping rule paradoxes, and in this case that was a bad idea. Bayesians don't have this problem at all. Bayesians decide what the probability of a hypothesis is based only on exactly the data that they see, based on the videotape of the observer flipping coins. And we've already seen now several times how you do this. You have a set of hypotheses, exhaustive and mutually exclusive. We'll call them H sub p. That's the hypothesis that the probability is exactly equal to p. And then we're interested in what is the probability of each of those hypotheses, probability of H of p. And we get it by Bayes' rule. The probability of H sub p given the data is the probability of the data given H sub b times a prior on H sub p. And in this simple example, we'll take the prior to be uniform or proportional to 1, and therefore the probability of the hypothesis given the data is proportional to p to the 9th times 1 minus p. That is to say, 9 heads followed by 1 tail. We put in the Bayes normalizing denominator here, and that's our answer. This is the probability distribution of each hypothesis, that is to say, of each probability on a single coin flip. And to a Bayesian, this curve just is the answer. We've seen this before. However, we're allowed to summarize the curve in various ways. In this case, when the question of interest is it a fair coin, so it should be at 0.5 here, or is it some kind of unfair coin, as it appears to be, with the maximum probability up here, a reasonable way to summarize this curve to somebody would be to say that the probability of it being fair, which is 0.1074, proportional, I should say, to 0.1074 on this curve, divided by the most likely result, which is up here, is about only 2.5%. And therefore it seems rather unlikely that this is a fair coin. Just because we're Bayesians doesn't mean that we're not allowed to compute tail probabilities as a means of summarizing curves. And so another way of summarizing this curve to somebody who's interested in was the coin fair is you could start at 50% here and ask what's the area under the curve to the left, that is the integral from 0 to 0.5 of the probability of the hypothesis given the data, and that comes out only about 0.5%. So you can say to your friend, there's only a 0.5% chance that the coin was biased between 0 and 0.5, whereas there's roughly a 99.5% chance that it's biased between 0.5 and 1. Here's an example where a Bayesian would get to do a much more subtle analysis, a more sophisticated analysis, by choosing a different kind of a prior. So suppose the data, instead of being 9 heads and then a tail, was just, you see the videotape and it's 10 flips of the coin and it's 10 heads in a row all come up. Well, we're allowed to use our prior knowledge of the world here. So you think to yourself, people have made me watch them flip coins before in my lifetime. And when they do that, 90%, 95% of the time, you decide, it's a nearly fair coin, so that's hypothesis A. But 4% of the time, it's a trick, and it's either a double-headed or double-tailed coin, so that'll be hypotheses B and C. And then maybe 1% of the time there's something else going on that isn't either of these. Because we're Bayesians, we have to have exhaustive and mutually exclusive hypotheses. So we always have to include something for, if it isn't something that we haven't already named, then it's got to be something else. So here's how we would do that analysis. Case A has a 95% prior. And in the case of case A, it's a fair coin, so the probability of seeing 10 heads in a row is 1/2 to the 10th, and that comes out this pretty small number here. In case B, it's a double-headed coin. Our prior on that is only 2% because it's half of the 4% up here. And however, the probability of seeing that data is 1 to the 10th, so we get the full 2% coming in down here. In the case it's a double-tailed coin, then the probability of seeing all heads is 0. And we have to decide what to do in the case of something else. Well, in the case of something else, we say there was just some unknown probability p on each flip, and the probability of what we see was p to the 10th. And now we're going to take a uniform distribution over that value of p. That's simply an expression of our ignorance, so we integrate that from 0 to 1 dp, and that gives this result here. Now, I sum these all up, and I renormalize them, dividing by that denominator, and here's how our Bayes probabilities come out. Notice that even though it had a quite small prior, only 2%, by far the most likely conclusion that we should draw is that whoever is taking the video of flipping a coin is probably using a double-headed coin. Now this may seem a little bit fanciful to you, but I'm actually trying to illustrate a kind of analysis which is sometimes called meta-analysis. It would be meta-analysis if we went back into the literature of coin flipping and actually, from a number of previously published papers, measured what the prior here should be, so that the prior would be informed not just by our vague prejudices on the matter, but by some actual research on it. Then, when we come to this experiment with 10 heads in a row, and we want to include that in the meta-analysis, we can include all these previous cases and do the calculation that I've shown you here. This is a good way to live your life if you're a person who likes to make bets. Be sure that you're betting on what you think you're betting on, and don't, by mistake, be betting on a two-headed coin. Now, can you remember that I promised you I would list 3 Bayesian criticisms of the tail tests, and the other 2 won't take as long. Criticism number 2 is that if there's more than one hypothesis, a p-value test can't really be used quantitatively to compare the probability of the 2 hypotheses. Now that's something that Bayes does very, very well. The problem here is that ratios of p-values don't particularly mean anything. You might have thought that if you have two hypotheses and one gets a very, very small p-value and the other gets only a slightly small p-value, that you know something about their relative probabilities. But take it from me, the formalism just doesn't work that way. You don't know anything about it. There is a way within the frequentist universe to say something about that, and that's called likelihood ratio tests. And I'll let you go look that up on Wikipedia or somewhere and learn about that. The reason I don't want to tell you much about that here is because as a Bayesian, there's just a very easy thing we do. We compute the probability of each hypothesis, and we can take the quotient of any two hypotheses, and that's the Bayes odds ratio, and that's how to compare by what ratio one hypothesis is more likely than another. The third, and in some ways most serious criticism of p-value tests, is what I call here the sanctification of certain magic p-values. So for example, in biology, it's generally agreed that if you do an experiment that has a p-value of less than 5%, that's a significant experiment, and it will be accepted by most journals and published if it's an interesting paper. Whereas if you get a p-value slightly more than 5%, you have failed to reject your null hypothesis, you haven't learned anything, and you haven't produced a publishable paper. But what's magical about 0.05? Where did that come from? On the one hand, if we insist on a p-value of 0.05, then 1 in 20 results are going to be wrong. That is to say, there is a probability of 5% that the null hypothesis is correct, and that nevertheless we get a value as extreme or more extreme as the one we measure. That's simply the definition of the p-value. So 1 in 20 results will be wrong, and you can imagine what would happen if we applied this uniformly across all fields and built nuclear power plants to this lowest standard. Maybe the null hypothesis is this nuclear power plant won't blow up. But on the other hand, a large majority of results that have a p-value of 0.1 may in fact be correct, and these could sometimes be acted on. And by requiring that the p-value threshold is any single magic value, we're essentially eliminating the nuances here, the ability to take seriously results that are not quite as significant as that threshold, and not take completely seriously results that are over the threshold, because they may just be the chance extreme values of the distribution of the null hypothesis. It turns out historically that this idea of, I'm calling it slavish adherence to certain p-values, particularly 5%, comes from Ronald Fisher, who is arguably the greatest statistician to have ever lived. His years were 1890 to 1962. But Fisher was a very inflexible man. Fisher believed that statistics should be left to the statisticians, and experimental scientists should simply follow protocols that the statisticians dictated. And Fisher looked into his mind or his heart or some part of his anatomy and decided that 5% was a pretty good number, and that scientists should simply call results significant if their p-values were less than 5% and call them not significant if their p-values were greater than 5%. There's an irony here because Fisher actually studied with Gossart, who we know as Student. And Gossart never approved of the p equals 0.05% rule. Gossart, you'll recall, was the master brewer at the Guinness Brewery. And Gossart understood that there's no single magical p-value that's suitable for all circumstances. In fact, it depends on the economic return that you expect, the relative cost of a false positive versus a false negative, of a success or a failure. And Gossart, in fact, understood what we would now call the field of decision theory. Fisher Perhaps he understood this, perhaps he resisted understanding it, but Fisher nevertheless felt that progress could be made better in science if there were magic values of p that were used to separate significant versus not significant results. There's a fun paper on this by Stephen Ziliak that, with the reference given here, you can look up on the web and read. It's a very interesting historical case, and we're kind of stuck with the way it came out historically.